Lecture 9.4, Analyzing the Magnetic Field of a Straight Current-Carrying Wire. In lecture 9.3, we calculated this magnetic field. That the magnetic field of a finite wire was equal to mu naught I divided by 4 pi z squared plus L squared square root into 2L. That's what we calculated. But because the video was getting so long, I broke off step 5. And in step 5, we want to analyze analyze and interpret this result. So let's do that. So this is a continuation of lecture 9.3. So the first thing that I want to look at is that the infinite wire, and what I really mean is that I have an infinite wire that carries current, its B field occurs in the limit L much, much greater than Z. Physically, this means that the observation point P is very close to the wire itself. So we want to see what that limit is. So the limit then shows the following. So in the limit, as L is much, much greater than Z, this will then be B of finite wire. And then my constants that I can pull out are then going to be 4 pi. There's a 2 here. And I'm really looking at this limit for z squared L squared square root divided into L. That's what we're really looking. And one of the things that we could see here is that if I ignore z and essentially set that to 0, then I really have 0 plus L squared times z, the square root that is, and then I'm only going to get a term that's going to be z plus L. So in other words, I can approximate this and write this as 4 pi 2 mu naught I. So this would then be 0 squared plus L squared. And of course, that's to the 1/2. And then I have L. And you can see here that the L's are going to cancel out. And the result is that I get a value that reads 2 pi z into mu naught I. In other words, in the limit of L much greater than Z, the finite wire now has a magnetic field that we can call the infinite wire. And of course, this is going to be an approximation. When I do this, it depends on the number of sig figs that we're talking about. And then I'm going to get mu naught times I. So this turns out to be a fairly important relationship for the reasons that I stated in the previous lecture. So now I want to compare this. So how good is this? Can I replace the infinite wire magnetic field with the finite wire magnetic field? So what we want to do here is that we want to compare these two magnetic fields graphically to separate their identities. Or let's say extreme cases for, let's say, L much, much greater than Z and Z much, much greater than L. So here's what we see. So let's try to draw a nice big graph to try to really show these differences here. So this is going to be the magnetic field relative to the Z direction. And of course, this is the Z direction right here. So let's separate the magnetic fields here. So when you look at the relationships, you could see that the finite wire and the infinite wire are both going to behave exactly the same. Okay, they're both going to behave as 1 over Z. So when I'm looking at this, I'm seeing that this guy, let's say that this is the finite wire, I'm going to get a magnetic field that then it's going to look something like this. And so I'm going to say that this magnetic field is the field of the finite wire. Now, what about the infinite wire? Well, what we know about the infinite wire is that we can see here is that the infinite wire functionally behaves as 1 over Z. So that's not the case for the finite wire. And both of the ends turn out to match really well. So if I'm looking at this thing, they match up pretty good, and then they separate, and then they continue to match up really well at the end. So what I'm saying here is that this guy is the finite, the infinite wire. So what am I finding here? You could see that there's good approximation for L much, much greater than Z, and for Z much, much greater than L. So where they really separate, so they separate somewhere in the middle range. Now, what's that middle range here? But you could see here is that right here, this is where you're seeing disagreement. So for a finite wire, unless you're not in that middle range, you can approximate the finite wire, but an infinite wire. Solution here. So what does it mean? So now let's focus on the infinite wire. That was the whole goal of what we wanted to do here. So the infinite wire magnetic field falls, I didn't put wire. So I should put wire in here. Falls off as 1 over z, as long as we don't spend too much time in the middle. Now, what does this mean? So the question that we're asking is that what does this mean, let's say graphically? Well, the thing that I would like here is that I definitely want this guy. And then I'm going to copy this and bring it down. And I'm only interested in the infinite wire, not the finite wire result. So I'm going to say that I have this here. So I'm going to get rid of all of this. Right? I don't care about any of this. I don't care about the green. I only care about the infinite wire. And when I'm looking at this thing, what do I actually see here? Well, for starters here, here's what I'm seeing. So, it might be worth looking at this graph twice. Yeah, I think I'm going to draw it one more time. And I'll try to make sense of this as I go along. This idea just came across. So here's what I want to look at. Like, I don't want to be at infinity, but I want to be really close to the wire. So if I'm really close to the wire, then this means here, let's say I pick this point. So if I look at this guy here, what I see is that if I pick this point, which is really small, and I go right over here, you're going to see here that I'm going to have what? A really large magnetic field because it has a really small distance. But as I get farther away, look what I'm starting to see here. Now, the strength of the magnetic field is starting to drop off. So now let's start putting in what I'm actually trying to do here. So note that this magnetic field is smaller than the previous one. So what does that mean? I have to look at the line density. So if I'm looking at a current, let's say that this is the current coming out. I don't know if I had it out or going in, but what I'm seeing here is that if I'm really close here, I have a small circle, I'm close to this, that tells me here that I'm going to have a large magnetic field right here. So this guy tells me about B. However, as I start to move farther out here, to here, the magnetic field is actually getting smaller. Let me make this a little bit bigger. So this guy's supposed to be smaller than the other one here. And as I continue to move along here, you could say here is that maybe I come all the way over to here. Now, if I start following this all the way out, So what I'm doing here is that I'm just counting squares here. So then this guy, when I look at this magnetic field, you can see that automatically the field lines are getting farther apart. And as they get farther apart, you're seeing here, I'm going to have to change colors to really separate it. You're seeing that the magnetic field is decreasing. So in this situation, the magnetic field is getting smaller. So just to be consistent, I'm just going to color code these so makes a little bit more sense here. Okay, so now if I go to one more value here, what am I going to see here? Well, if I get farther out, you're going to see here is that if I come all the way out to here, and then I follow this guy, so now I'm counting 5 squares. So this is 1, 2, 3, 4, 5. You're seeing here that then the magnetic field, oops, is really getting farther away. And that's because the magnetic field is now smaller. So in this case, this guy is now smaller. That's what we mean by an inverse square law. And we can clearly see that as we spread out, you're seeing the field line spreading out more. So as one moves away from the wire, the field weakens in strength and field lines get farther away. So now let's go to the next thing. This is one of my favorite parts of analyzing this. And the question that I'm asking is this: what are the differences between a charged line versus a current carrying wire? What is the difference? And we're going to see that we could break it up into two pieces. This can be broken up into two pieces. As we're going to see here, one of them is that they have the same functional form. But are radically different. So we want to look at those details. And the other one here is that now that we're looking at fields, we should be able to analyze the divergence versus curl behaviors. Because we've calculated the magnetic field, we know exactly what it's supposed to look like, just like we've calculated the electric field that way. So let's start analyzing this. So the electric and magnetic fields of an infinite wire have the same functional dependence. And this is because both have the same magnitude of the displacement. However, that is where the similarity ends. So let's look at these. So I imagine that I have a wire that's infinitely long. And so let's say that I color this guy gray. I have the exact same wire, and I'm going to have the exact same point P right here. So this is going to be my point P right there. Now, because I need to do this for the other one, there is a separation between these guys. So I should be able to look at these guys over here and sort of like make a decision on what am I actually seeing. So if I have a charged wire, maybe I should move these down a little bit so that I have clear separation of them. So this is going to be a charged wire. So if I look at a charged wire, that means here that this guy here has to have a certain amount of charges on there. And if it's infinitely long, it's going to have an infinite amount of charge. Now, if I look at this guy, I'm going to have an electric field that's then going to point in that direction. And so when I look at that electric field, the electric field of an infinite wire, which is L much greater than C, the same thing, we can approximate this as 2 pi epsilon Z into the linear charge density. In other words, this is proportional to 1 over Z. Now, I can say the same thing for a current carrying wire. A current carrying wire what happens here is that I actually have electric charge that's moving through the wire. So if I look at the right-hand rule, if I look at R and I look at I can calculate where the direction of that magnetic field is. And what I'm going to see here is that the magnetic field points inwards. And as it points inwards, I can write the magnetic field, which we just calculated. And this is an infinite wire again. And I can approximate that by writing that this is then going to be mu naught I over 2 pi Z. And this will be proportional to 1 over Z. So you could see that, yes, they have the same functional form. But that's where it ends. In the situation of a charged wire, there is no electric charges that move. They are static. Over here, if we have a constant, current, that means here that the amount of current coming in, so this tells us here, is that the current in must equal the current out. That immediately makes the wire neutral. If the same amount of charge is coming in as going out, constant current immediately tells you that it's neutral. So then guess what? So if I have no moving charge, then no magnetic field can be produced by static charges. So a charged wire only has an electric field and no magnetic field. So once again, a charged wire has a non-zero electric field and a zero magnetic field. So you could see that I'm trying to hit points here. Now I can do the same thing here. So in this situation, if the current carrying wire is neutral, then it has no electric field. On the other hand, a current carrying wire has zero electric field and a non-zero magnetic field. So as soon as you write down the functional, everything changes about this thing. Now let's go to the last piece, which I think is equally as interesting. So over here, we were talking about the same functional form, but after that, it radically changes. It does. Now we want to analyze the divergence and curl behavior. So let's look at that. So maybe I should write divergence and curl. So other major differences is the behavior of the field lines. So what is the difference here? So a big difference here is that we know that electric fields start let me be careful. I said electric fields, but I really should say electric field lines. Electric field lines start at the charge, the charged wire, and diverge away from the line charge. These field lines never come back to the line charge. They point out radially and they're never going to turn. So they come back, they never come back to the line charge again. So what do we say? They do not curl back into themselves. So if I look at my picture again, I think I still have the wire. Let me see. Oh, I do. Check this out. So here's my wire. So when I'm looking at this, I'm going to take my P away here. And so if I look at this, I have my charge set up on this. Now, if I look at the fields, what are the fields doing? They are pointing outwards. So remember, I'm thinking about an infinite one, so I got to be close to it, but they are pointing away. And these field lines, they are not coming back. So the way we actually say this here is that, yes, we think about Gauss's law, and in Gauss's law, what do we say here? If I put in a Gaussian, what I'm finding here, right, here's my Gaussian right there. I'm seeing that there are field lines that are pointing through the surface, right? As they're poking through the surface, that immediately tells me that I have a flux. So that tells me that the electric flux is not zero, which then means that del dot E is not zero. There is enclosed charge. So in other words, E fields diverge. On the other hand, we've already said that these field lines do not come back to the line charge. So then we could immediately say that if that del cross E must be zero, and that tells us because E fields never circle back to the line charge. Magnetic fields are just the opposite. Magnetic fields are just the opposite. Magnetic fields, magnetic field lines are just the opposite. It is clear that magnetic field lines never start at the current carrying wire. And poke outwards. What they do is circle around current around wires and curl back into themselves, forming closed loops. Therefore, we have to say this. The magnetic field of, of the wire does not diverge, but instead curls around. So if I look at my picture here, there's two pictures that we can look at. I can look at this picture. So if I'm looking at this guy here, what am I seeing? I have a magnetic field, and it's circling around. Now, as it circles, my magnetic field lines are getting farther and farther apart. But they're always circling into themselves. And in this case, I have a current that's moving upwards here. Another nicer way to write this so that we can apply to what we're talking about is that now, let's say that this is my current right here. Okay, here's my current. So we know that we have magnetic fields that are doing like this. Oops, I think I'm going the wrong way. Yep, this current is wrong. So it's got to be going in this direction, and this one's got to be going in that direction. So when I'm looking at this, let's now form a Gaussian. So if I come in here and I form a Gaussian, right? So this right here is a Gaussian. So what am I finding? Well, look at the flux in. The flux in, I could count the number of wires. It's going to be 1, 2, 3. So I have 3 lines coming in. And then if I count the number of lines going out, I also have 3 lines. So that tells me that the net flux here is 0. And because the net flux is 0 here, we could then come again to Gauss's law. And Gauss's law says that if the flux is 0, then that means, you know what, I'm going to bring this down because I'm running out of space. So if I bring this guy down here, I could then say that if the flux is 0, that means here that del dot B is 0, which then means that magnetic fields do not diverge from the line charge. However, del cross B is not equal to 0 because we know that there's an enclosed current, which means then that magnetic field lines do curl back into themselves.